Welcome to the last video in my Chem 2 OER series here. This is coordination chemistry, where we're going to learn about some slightly new bonding motifs that we really haven't looked at previously. If you've watched every video in this series, thank you so much. I hope that you've enjoyed it and that it's helped you get through your Chemistry 2 curriculum or just understand chemistry better. I think that coordination chemistry here is a great way to wrap up the course, as it really illuminates some of the future topics you may look at if you go into inorganic chemistry, and are some notations that could be pretty confusing if you haven't seen them before, but really will come up if you pursue the chemistry literature. And so just understanding what exactly you're looking at, I think, is really helpful. All right, if you did make it through, thank you again so much, and I hope you enjoy our last video here on coordination chemistry. As we get started learning about coordination chemistry, it's essential to start with electron configurations of transition metals. And remember that we have a few exceptions within the transition metal series, but we're going to start with just general ideas about transition metals. So first of all, transition metals, these are in the middle of the periodic table, and when we're looking at an electron configuration, we want to start with the noble gas configuration that's the largest contained within that metal, and then we have a certain number in the S subshell, so that would be 2 generally for whatever S sublevel that'll be, and that depends on what period your transition metal is in. And then you'll have that -1 d orbital. So if it's 5s, you'll have the 4d sublevel. And hopefully this is a good refresher of what the numbering system of these sublevels should be. For example, what is the electron configuration of iron, chromium, and copper? And here would be a good chance to pause the video and see if you can refresh your memory on electron configurations for these transition metals. All right, hopefully you were able to come up with an answer here. The electron configurations are as follows. So for iron, we start with argon. That's the largest noble gas contained within iron. Then we go to the 4s sublevel, and there are 2 electrons there and 3d6 to get up to where iron is on the periodic table. Now, chromium and copper, we have a slightly different trend where we have 4s1, 3d5. And this is because when we have a d subshell that's either half full or very full, completely full, we have a exception. And basically this is because the 4s and 3d sublevels are very close in energy already. So if we can fully or half fill the d sublevel, it will do so by putting that second s electron into the d subshell. Some exceptions are as follows, and again, this is all about getting a half full or very full d sublevel, and that's something that will definitely come into play in your study of coordination chemistry. If we have a larger noble gas, don't forget that F sublevel that's in the middle. We often don't deal with the F level because this is that long row of atoms that's too high in the periodic table. That's kind of an insert within the periodic table. But if we have a particularly large metal, it's important not to forget these. And we're really not going to deal with the F level. We're not going to break up this F subshell, but it is important to know that the electrons are there and that they're not going to break up. Really, the transition metal study that we're going to do is going to focus completely on the D sublevel. So getting the D count is really the motivation for this study here. What is the electron configuration of tungsten? And if we look at this one, we'll see that there is this F subshell, and we're going to have to fill all the way through that and then get to 5d4. So hopefully this is what you're able to come up with as well. When we look at gold, again, this is that same exception that we discussed previously, where it can obtain a full D sublevel by promoting one of the S electrons into that D subshell. Again, we mentioned these F sublevels just to make sure that we're counting those electrons properly. We're not really going to need to consider breaking up that F sublevel or anything like that in this video. Okay, again, there are exceptions to filling rules. The idea is that 4s and 3d are very close in energy level, and this closeness in energy level is the exact same if we were dealing with 5s and 4d as well. So if we add electrons to a d sublevel, that causes the d energy level to drop a little bit. And because they were so close already, even though we're adding into s first, occupying the D sublevel makes D a bit lower energy, and now that is the lowest energy sublevel. Again, we still want to fill S first, but this is really important to consider because when we start taking electrons out, the highest energy electron is most often going to be in that S sublevel. And so for a take-home rule, we are going to, generally speaking, take out of the S sublevel before we start taking out of the D sublevel. Again, half-filled, completely filled D shells gain additional stability, but this idea of removing from S before D is going to apply regardless of whether that D shell is half-filled or completely filled or anything like that. Here is the electron configuration for chromium. Again, we start with argon and we end up with 4s1 3d5. And hopefully this diagram, this orbital diagram, looks familiar as well, where we show the electrons as arrows. And maybe this helps to reinforce the idea that half-filled subshells are extra stable. It's nice to have every one of them filled with all the electrons spinning in the same direction. Half-filled orbitals gain additional stability. Okay, what is some more off-trend behavior? Well, we said when they're filled, we're going to remove from 4s first. So let's consider iron. Iron is argon with 4s2, 3d6. This is just regular iron in the initial state. But if we have iron 2+, we're going to remove those 2 electrons from 4s before we remove from 3d. And therefore, we're going to be left with 3d6. And if we have iron 3+, we're going to have 3d5 because we're removing yet another electron, and this will be the electron configuration for iron 3. Okay, so with this in mind, go ahead and pause the video here and think about, well, what about for zinc and for zinc 2, the zinc ion? What are the 2 electron configurations for those? Go ahead and start with zinc. Then for zinc 2, you'll remove the 2 highest energy electrons and see what you come up with. All right, hopefully you got a chance to try out those electron configurations. Here's the configuration for zinc. Again, we start with argon, then 4s2, and then 3d10. We fill up the whole 3d sublevel. And when we remove electrons, which ones are we going to remove? Do we want to remove the 4s or the 3d? And the answer is that we want to remove 2 electrons, and we're going to remove those 4s electrons. And therefore, what we're left with is argon and a completely filled D sublevel. This explains why zinc only forms +2 ions, because that D sublevel is so full that it's really not going to want to break that one up. Again, full sublevels are desirable. They're additionally stable. This is the origin of why noble gases are so stable. And so it's not going to want to form a +3 ion naturally because that would require breaking up that D sublevel. Again, what we see here is that not only is this the case, but it also doesn't want to keep a half-filled 4s sublevel, and this zinc 2 is really the only ion that zinc likes to form. Okay, so this gets into the idea that oxidation states for transition metals are often not just one. You know, zinc only likes to form one ion, but a lot of metals like to form multiple ions. And this is getting into the study of coordination chemistry and the study of complex metal ions, because different metal ions often have different colors that are associated with them, and different complexes have different colors associated with them. And we're not going to cover this completely in the video, but this is really the launching pad for the rest of the curriculum that you're going to study in coordination chemistry, or if you're using this as an introduction to inorganic chemistry, where all of this will come into play quite a bit. These d electrons, how they're arranged, have a huge impact on the color that these species will exhibit. And the first step to understanding that electron configuration is knowing how many electrons you have in the d sublevel. In other words, the d count. So that's really what we did just now, is when we were looking at iron 2 and iron 3, we said, well, iron 2 was 3d6 and iron 3 was 3d5. So we would say iron 2 is a d6 metal and iron 3 is a d5 metal. That's to say the number of electrons in the D sublevel, and is a very important launching pad for coordination chemistry. Coordination chemistry is interesting because we have a lot of unique structures that we may not have seen before, and they're all centered around these transition metals. So again, where we've had these Lewis structures previously, like in object A here, where we have methane and we have sodium chloride, these are more traditional structures. In complex ion formation, we'll have things like a metal in the center, like in B, we have the scandium in the middle, where we have 6 waters that are arranging around it. These D metals are making for a octahedral complex that's able to accommodate this water bonding, which is not exactly like something that we've seen before. So that's another unique part of coordination chemistry. We can have linear geometries, we can have ions with overall charges similar to polyatomic ions, but not exactly the same. And if you continue with inorganic chemistry or continue on in coordination chemistry, these will definitely be studied. But for an end to this video and to wrap up learning about coordination compounds, Here is an example of such a compound where we have first this copper with 4 ammonias. So this is a complex ion. It's kind of like a polyatomic ion, but it's based around a metal center. And we have Cl2. So this is 2 chlorides that are the counter ions here. So this is a coordination compound. It contains a complex metal ion, that's the cation here, and it contains some counter ions, that's to stabilize and to make for a charge-balanced ionic compound, which we've definitely seen before here in chemistry. Again, here's the complex ion, and here are the counter ions. Together they make for a coordination compound. But when we see this just as written, what's important to recognize is that we have this central metal here, that's that copper, and it's bonded to 4 ammonias, which in this case are called the ligands. And so this is a rather different bond. So to speak, it's a bond where both of the electrons come from the ligand. So remember, ammonia, NH3 has a lone pair. Copper is generally wanting electrons, so both of those electrons from ammonia will bond into the copper, and that makes it slightly different from other covalent bonds where we have a more even sharing, electrons coming from different species. And here, it's important to know that they're called ligands, and the central metal is going to have a certain oxidation number, which is going to determine its d electron count, which, as we mentioned, was so important. So again, let's break down this complex ion a little bit. It is this one, right? Copper is the metal center, and we have 4 ammonias, and the overall charge is +2. What this means is that the central metal here has a charge of +2, an oxidation number rather of +2, because it's bonded to 4 ammonia ligands that don't have a charge. And this is where it's really important to have recognized many of the common species that we deal with in chemistry, because if instead we had something like F4 here, 4 fluorides, it would be important to recognize, well, if that's fluorine all by itself, it's going to be fluoride. It's going to be existing in its anionic form. It's not going to be fluorine, elemental, and monatomic. It just doesn't exist like that. So even though the charge won't be stated there, it'll be important to recognize that the charge does exist, and that will affect the charge or the oxidation number of the central metal. Okay, let's take a look at another one here. So here is another coordination compound. We have chromium with 4 ammonias and 2 chlorides counterbalanced with a nitrate. And the question here is, what is the oxidation number of the metal? So kind of a challenging problem, but I would recommend that you pause the video here and give it a try. Start from the outside and work your way in. So the first thing you should do is say, well, what's the charge on the complex ion within the square brackets? And that we can determine based on the anion, because we know that the charge from the two of them have to be equal. Then we want to know, well, what are the ligands? Remember what I said about the fluoride earlier, and remember that chlorine is pretty much the same. Is it going to be Cl- or is it monatomic chlorine? It's not going to be diatomic chlorine linked in here as a single ligand, even though it does kind of look like that. So keep that in mind when you're coming up with the charge contribution from each of the ligands, which will determine the oxidation number for that chromium, and that's what we're looking at here. Once we have the oxidation number, if it's, chromium of whatever charge, whatever oxidation number, we'll know that it's missing that many electrons, and therefore we'll be able to determine the d electron count. So I know that's a lot, but give it a try. I'll break down the solution in just a second, and go ahead and pause the video. All right, hopefully you're able to give this a good try and at least get part of the way through. The complex ion has a charge of +1, and that's because the nitrate has a charge of -1. It's NO3. This is nitrate. We know this one well. It's got a charge of -1. The metal ion at the center of this complex ion is chromium, and so that's what we're going to be dealing with in the end. The counter ion, as mentioned, is this nitrate, and it's got 4 ligands. 4 are ammonia and 2 are chloride, Cl-. And it's very important to recognize here that when we see this Cl2, that means 2 chlorides. It's not an elemental chlorine bonded in as a pair. It's not 2 different elemental chlorines or chargeless chlorines. It's chloride. That's the most common form of this chlorine here, and that's what we want to expect when we see this notation. The ligands contribute -2 charge to the oxidation number of this complex ion, so eventually the oxidation number of the chromium, because those 2 chlorides have a charge of -1, and there are 2 of them, therefore -2 is the charge from these ligands. And therefore the central metal must be 3+, this must be the oxidation number of the chromium, because it needs to add up to a +1 overall charge. That is to say, it needs to overcome the 2 negative charges that the chlorides bring, and in the end needs to be +1 because that was determined to be the charge on the complex ion based on its counter ion, which was a nitrate. All right, so this is just a really brief introduction to coordination chemistry. I hope that it's a topic that you found somewhat interesting. It really leads to a lot of questions, a lot of, entire courses on inorganic chemistry. So if that's what you're heading towards, definitely use this as a jumping off point. Remember, the d electron count is very important. And if we want to get the d electron count, we need to know the oxidation number. Not exactly the charge, because when they're in complexes, that charge is not isolated, so it's an oxidation number, it's not a charge. But without knowing how many electrons this central metal is lacking, we'll never be able to get the D count, and that D count is going to be so important moving forward for transition metal chemistry, inorganic chemistry, and anything you're looking to study involving the transition metals. All right, that is our last video here in this Chem 2 OER. I hope you've enjoyed it, and if you haven't checked out all our other videos, I hope you give them a try.